Okie dokie. So we're going to talk now about in section 10-2, so get into chapter 10 here, and this one we'll talk about correlation. And so we're just going to talk about for chapter 10 this section, then the next section, and those two will be enough for some most important ideas with correlation and regression. All right, so some key concepts here are in part 1 of this section introduces the linear correlation coefficient R, something you're going to be calculating, which is a number that measures how well paired sample data fit a straight line pattern when graphed. Notice it says paired, so like XY pairs is typically what we'll use. And using paired sample data, sometimes called bivariate data, we find the value of R, usually using technology. Then we use that value to conclude that there is or is not a linear correlation between the two variables. And correlation is a way of saying an association or a relationship of some sort. More key concepts in the section we consider only linear relationships, which means that when graphed, the points approximate a straight line pattern. And in part 2, we'll discuss some methods for hypothesis testing for correlation. But hypothesis testing ideas are in here throughout most of the section. So for part 1, starting with some definitions. So a correlation exists between two variables when the values of one are somehow associated with the values of the other in some way. So again, basically there's an association or a relationship of some sort. Now, more specifically, a linear correlation exists between two variables when there is a correlation and the plotted points of paired data results in a pattern that can be approximated by a straight line. So now why these particular correlations are so important in statistics is because they are particularly useful for predicting trends and seeing just different associations between paired data for two different variables. So we can often see a relationship by two variables when we construct a scatter plot. And so, for example, like looking at a scatter plot like this one here for A, then this one has a fairly strong positive correlation because it looks like as whatever these values are for X, as they increase, it looks like the values for Y also increase. And so these ones we'd say follow fairly straight lines. That's why there's a good positive correlation there. And these ones in this picture for B also follow a straight line fairly well. And just notice if we were to draw a line here, they'd have a negative slope. And that's why we're saying this one has a negative correlation. And this one is actually an even stronger correlation than A. And we'll get to why we can say for sure that's stronger. Then you might get something like this in part C, where it looks like the dots are just absolutely all over the place. There's not really any straight line pattern or anything like that. So this is where we just say there's no correlation. Now, even though we'll focus on linear relationships, it's possible that variables may have nonlinear relationships, like this one here, where it looks like a parabolic relationship of some sort. And correlation coefficients are possible for nonlinear, but we're going to focus on just linear. So now some requirements for linear correlation is just the sample of paired XY data is from a simple random sample of quantitative data. So simple random sample is a common requirement. And upon visual examination of the scatter plot, we must confirm that the points approximate a straight line. And then the outliers must be removed if they are known to be errors. The effects of any other outliers should be considered by calculating R with and without the outliers included. So basically, number 3 is saying that outliers can affect the correlation coefficient quite a bit. Now, there's a fair bit of notation here just because there's a fairly heavy formula for calculating correlation coefficient. That's something you won't have to use, but you can use. And so I'll just run through just real quick this notation. So n is still going to stand for our number of pairs of sample data this time. So it's still a sample size, but it's pairs of sample data since we're looking at paired data. That sigma is just denoting that we're going to be adding things when we use formula. If it's sigma x, it's just sum of all the x values. Sigma x squared, this means you square all the x values, then add them up. If it's the sum of x and squared with parentheses like this, that means add up all the x values. Once you have that sum, square it. Then if it's the sum of x, y, this means take each product of the pairs of x values with the y value, get all of those products for those pairs, then added all of those up. And then just lowercase r is what will stand for our linear correlation coefficient of the sample data. Understand? And then this symbol right here looks like a p. It's actually a Greek letter rho. So this is the linear correlation coefficient for a population of paired data. So that's kind of more what we'll use when we get to populate hypothesis tests. Now this is the monster of a formula for calculating the correlation coefficient. And so this one uses just all the x, y values directly. And then this other formula right here is a different formula for calculating the correlation coefficient. This uses, if you were to convert all the x and y values into z-scores. But again, technology can and should be able to compute the r values for any sets of data we use. So you can use these formulas if you want to, but I encourage you more to use the technology. It's just more efficient and makes more sense to use the technology. And there's one other formula that you can use for finding the correlation coefficient. This is the one that I'm a little more used to and prefer over the other two. Basically, this just means take every x value, subtract the mean, get that difference. Take every y value, subtract the mean, get those differences. And so you multiply those differences, then you add up all of those differences. And then, so that's on top of the fraction. So on the bottom of the fraction, you've got two square roots, so one of all the x values minus the mean. Take those differences, square them, then add them up. Then you square root that sum, and you do the same thing for the y's. Once you would divide those, you would still be getting the same correlation coefficient. But of course, there is some recommended technology, and I highly recommend some of the applets that we have available for StatsMedic, which are linked in our Canvas page. And so there's three that can all pretty much do the same things for any of the concepts in this section and the next section. And so I'm going to show you where those are at. And just know there's also a table of values that we're going to use for this section, so I'll show you where to find that also. So when I go to a Canvas page, now to find those applets, I'm going to go to Pages, View All Pages, then I want to go to YouTube and Other Tools. I'll go to that StatsMedic Simulations. And so here's where I can find all the simulations and applets. Now the ones that will be useful are under this section here, testing and correlation or testing a slope. And I can also use under the traditional inference, I can use linear regression t-test. All three of them will be able to do the same things for you. And then as for the actual table values we're going to use, it's on that same page in Canvas, and you just go down to tables and you click on linear correlation 10-2. It'll look like this once you pull out that table. Okay, back to some of the examples. So using table A-6, if the absolute value of the computed value of R exceeds the value in table A-6, conclude that there is a linear correlation. Otherwise, there is not sufficient evidence to support the conclusion of a linear correlation. So this will be one way we can say if there is a linear correlation or not. So again, we'll calculate a correlation coefficient value either using technology or those big formulas. And if it's bigger than the critical value, then we conclude there is a correlation, which when we do the hypothesis tests is like rejecting H0, which you'll see in a little bit, because H0 will usually be that there is no correlation. And so this is actually similar to the critical value method of hypothesis testing from chapter 8. But when it's talking about a critical value from table A-6, it's referring to all these values in these two columns, because all these values here are considered critical values for linear correlation, and they'll just depend on whether we're using a 0.05 significance level or a 0.01 significance level for each problem. And so basically, if our computed values exceed these, depending on our sample size, we conclude there is correlation or not. Now, you can also use software to compute the p-values. Now, if the computed p-value is less than or equal to the significance level, then we conclude that there is linear correlation. Otherwise, there's not sufficient evidence to support the conclusion of a linear correlation. So again, if the p-value is less than or equal to that significance level, which we can still say is alpha, then we conclude there is correlation. So still, like, we'd be rejecting a null hypothesis of there being no correlation. So this is still similar to the p-value method of hypothesis tests from chapter 8. As a caution, know that the methods of the section apply to a linear correlation, and it's possible that there will be other types of correlations, say exponential or quadratic, but we'll focus on linear for this chapter. Now, some properties of the linear correlation coefficient are is that it'll always be between -1 and +1. And if all values of either variable are converted to a different scale, the value of r does not change. The value of r is not affected by the choice of x and y, and we can interchange all x and y values, and the value of r will not change. And again, r measures the strength of a linear relationship. It's kind of its main purpose. And R is very sensitive to outliers, so again, that's why if there are any outliers, we want to not include them in our calculations. Okay, so now to finally start with an example here. So this is a table of some shoe print, sizes and then heights from 5 males are listed below. And now we're going to use the computer or calculator to find the value of the correlation coefficient R. So again, when you do that, you can use those formulas or you can use some of the Statsmatic applets. I would recommend the applets again still. Yeah, so just a quick requirement check. So the data was from a simple random sample of quantitative data. And when we plot the points here, they can follow roughly a straight line pattern. Then we're not seeing too many outliers. Notice the condition for needing to follow a straight line pattern can be a little loosey-goosey because these aren't super straight, but we can say they're close enough. Now, there are some other technologies you can use, of course, plenty out there to find these correlation coefficients. I'm going to show you how to use the Statsmatic applets to find it. So basically what I would do is I would take these data values and I'd plug them into one of the applets. So let's see, I'm going to, and it wouldn't matter which one I click on, testing correlation, testing a slope, or the linear regression t-test. Either one will take me to this page first. And here I can type in what the variables are. Now, again, it doesn't really matter which variable you put where. Explanatory is usually the x variables. And so I just went ahead and put shoe prints as the explanatory variable. And the way you put in the data here is you have to actually type it in. So I pasted it in here so you don't have to watch me type all that in. Notice it says separate by commas or spaces, or you can do both. So once I've got all those values typed in, so those same data values here, then I just click begin analysis. Gives me that same scatter plot. Keep scrolling down, and then I can just go ahead and click calculate correlation. So it gives me this is the correlation coefficient value of 0.591. Which, looking at these other technologies, it's essentially the same correlation coefficient values, 0.591. And so again, technology is highly recommended for when you find those correlation coefficients. If you want to use the formula, then I'd refer you to pages 498, 500, and 501 for seeing the formula in the textbook, and then also an example for how to use it. So we found previously that that correlation coefficient is 0.591. So now we're going to proceed to interpret its meaning. So our goal is to decide whether or not there appears to be a linear correlation between the shoe prints and the heights of people. So we can base our interpretation on a p-value or a critical value from table A-6. I'm going to save that for the next part of these videos.